Well, now let's consider an endothermic reaction, which is a reaction in which energy is absorbed. Here's an example. NH3, which is ammonia gas, can decompose to make nitrogen gas and hydrogen gas. And let's suppose that 50 kilojoules of energy are added as reactants to make this happen. Well, we can make a potential energy diagram in which the approaching ammonia molecules, imagine two coming together, beginning to collide and storing potential energy. They form an activated complex, high energy, short-lived, and then they fall apart. But the products of this reaction actually contain more energy than the reactants did. Some energy has gone into the system. Well, the energy of the activated complex is 200 kilojoules, but the energy that was needed to be put in, the activation energy, is only 90. That's the length of that arrow, that green-yellow arrow. The change in enthalpy, the energy that went in overall, is just that bright pink arrow, 50 kilojoules. And that's an endothermic reaction. So now we've seen that activation energy is present in both endothermic and exothermic reactions. The size of the activation energy represents a barrier. The higher the size, the greater the activation energy, the greater the barrier to having an effective collision. The one on the left with a low barrier, it's a fast reaction, and the one on the right will be slow. I'm just saying that the larger the activation energy, the slower the rate of a reaction, all other things being the same. I also want to talk about the total energy of a system. That's the energy that's stored, potential energy, plus the energy of motion. Here's a potential energy line, similar to what we've seen at endothermic. Well, the kinetic energy goes in an opposite way. As potential energy goes up, kinetic energy goes down, and vice versa. But the total energy of the system is always constant. Now, the energy term can be written right into the chemical equation, as we saw a little bit earlier, or it can be shown separate from it. Here's an endothermic reaction. Let's say that 60 kilojoules of energy add to A and B to make C. I can use mathematics to move that energy term to the other side, in which case it's showing as a minus, or I can just separate it completely and show that the delta H is plus 60. Now, for an exothermic case, energy is produced, but I can also say that energy is subtracted from the reactants here, as in this second one. Or I can say that the reactants make products and the change in enthalpy is negative. Well, that's it.